Hey guys, so in case you haven't already guessed from the title, I have my AP Physics 2 exam on in 3 days from now, so on June 10th, and I've hitherto not really studied for it much since school ended, so I'm going to begin cramming for it, and yeah, so this will be the first cram session. Also, I'd like to shout out my little sister, Mango Potato. That's her YouTube name. It's like capital M and capital P, no space. And yeah, she also makes physics videos. And yeah, so without further ado, I'm gonna start off with the order I recall learning these concepts in school. So first, we're gonna be, well, I'm gonna also be, well, it's not really a learning thing. It's more of me reviewing it. But I'm gonna be reviewing static fluids. And yeah, so also, so the first thing about static fluids is, well, it's pretty self-explanatory, just fluids that don't move, and then the next chapter will be obviously on fluids that do move, but yeah, so, and also another thing is that, actually I think I skipped a chapter. I'm using the textbook right now that I used in school, but I think the first chapter is actually gases. Can you just double check something? Nah, actually, I think it's better if we guess before throwing dynamics. Okay, yeah, so I'll just start off with this, so static fluids. And yeah, so the first major concept that's introduced in the book and that I recall learning is density. And in mechanics, density is simply the amount of mass stored in a given volume. So denser objects have more mass in a certain volume, whereas, like, for instance, if you had um, well, let's just use the age-old example of like a ton of steel and a ton of feathers. Actually, let's not use a ton because that's technically a measure of weight. So let's use a kilogram. So if we have a kilogram of steel and a kilogram of feathers, then the steel is going to occupy much less space because less mass is needed, or less volume is needed to store that mass since it's a lot denser. So the formula for density is just rho, which is just a Greek letter, and it's equal to mass over volume. And yeah, and you can actually find the density of irregularly shaped objects by sinking them and sort of timing how fast it takes to sink. And you can also see, okay, so one thing that Archimedes discovered, I apologize in advance to him posthumously in case I butchered that. He's this Greek scientist, but he realized that if you put like something in water, so let's just say I have a rock and the rock has a volume of, I don't know, X, and the water occupies a volume of, actually let's add subscripts to avoid any sort of ambiguity. But the water occupies a volume of Y. Then if I add the rock in the water, it'll actually displace the water. So now the new volume of the water and the rock will be X plus Y. So you can actually use this to find the volume of like irregularly shaped objects because obviously not everything in real life is going to be a cube or a sphere. In fact, most things are just irregularly shaped. So that's one way you can find volume, and that's what was discovered by the ancient Greek scientist Archimedes. And yeah, so density is the amount of mass in volume, and you can find how much volume something occupies by putting it in like a fluid like water. Oh, actually, not just any fluid, an incompressible fluid. So generally, liquids are incompressible, so it works like for water or other liquids. But gases are also fluids, and gases are typically not incompressible. So you couldn't use this trick with gases. Okay, let's now do a practice problem that uses densities. and this is in the book. But okay, so Saturn has the lowest density of all the planets in the solar system, and according to the poem, it gives us that the mass of Saturn. Actually, let me just clean all this stuff up. I don't know why it's zoomed out so much. Something, yeah, I don't know why, but okay, whatever. So the problem gives us that the mass of Saturn is about 5.7 times 10 to the 26 kilograms. I believe Earth's is like 5.97 times 10 to the power 24. So it's like two orders of magnitude above Earth's mass, or in other words, like 100 times more massive than Earth. And it also gives us that the volume of Saturn is 8.3 times 10 to the power 23 meters cubed. And it apparently has the lowest density of all the planets in the solar system. Okay, and then it says here, the average density of a neutron star is 10 to the power 18. So I'll just write that out. See, I'll put the subscript. Okay, it's 10 to the power 18 kilograms per cubic meter. Okay, and compare the mass of a ping pong ball filled with material from Saturn with that of the same ball filled with material from a neutron star. An empty ping pong ball has a diameter of, okay, so it's 0.037 meters, and it says that we should just round the radius to 0.02 meters, which is a lot more convenient. So I think let's do that. And it also has um, a mass of 2.7 grams. And I'll just convert this for the sake of consistency to kilograms. And I'm too lazy to write out a decimal, so let's just use scientific notation. So this is 2.7 times 10 to the power negative 3 kilograms. Okay, and and this is for an empty ping pong ball, by the way. So for the mass. And now we're gonna fill it with material from both a neutron star and Saturn, and compare the masses. And I'm assuming from the problem it wants us to assume that like the shell has like a negligible width because they never specified the width of the shell, so I'm just gonna assume that. Okay, so then we know that the mass of our filled ball is obviously just the mass of the material inside, whether that's like from a neutron star or Saturn, plus the mass of the ball itself, like the hollow exterior portion. And we also know from using our density formula from earlier, since we said density is mass over volume, this then implies that the mass of the material inside the ping pong ball is simply the density of the material times the volume of the ball. And yeah, okay, and since ping pong balls are spherical, the volume would really just be the density of the material times 4 thirds pi. Or sorry, this would be the mass, but the volume itself would be 4 thirds pi r cubed. And we said r is 0.02 meters. So yeah. And we're assuming that the plastic shell has negligible volume. So in that case, we can write this initial equation. Okay, that was a terrible circle. But I'm referring to this initial equation. We can rewrite it now as the mass of the material. Actually, no, that's the part I want to rewrite. So let's change it now to the mass of the ball plus um, the mass of the material, which is just equal to the density of the material times 4 thirds times pi times 0.02 cubed. And actually these should be brackets. But yeah. And so all we really need to do at this point is just plug in what we know for both the neutron star and Saturn. So if we're going to do the neutron star first, so let's say neutron star ball, well that would just be the mass of the ball in either case is really just well, oh yeah, 2.7 times 10 to the power negative 3 kilograms plus, and it gave us the density, which is 10 to the power 18 kilograms per cubic meter times 4 thirds pi times 0.02 meters, which is the radius cubed. And you can see that the units neatly cancel out to give us units of kilogram, which is consistent with this. So we know that this formula checks out via dimensional analysis. And so if we compute that, we get that the ball would be a whopping 3.4 times 10 to the power of 13 kilograms, which is a lot. That's like 34 trillion kilograms, which is, okay, I can't think of anything to use for reference, but it's like not as massive as the Earth, obviously, but it's for something the size of a ping pong ball, that's pretty heavy. Okay, and so that's for a neutron star. And now for a ball filled with material with the density of Saturn, we basically do the same thing. This time they didn't give us the density, so we have to use our formula for earlier that rho is equal to m over v. And if we do that, so the mass for Saturn that they gave us is 5.7 times 10 to the power 26 kilograms. The volume they gave us is 8.3 times 10 to the power 23 cubic meters. And yes, so this would just be equal to the density. And actually, let's move 4 pi over 3 to the front so it looks neater. And so all we need here is the radius cubed. And since we're just putting in the ball, the radius is the same in either case. It's just 0.020 meters cubed. And if we find this, it should be about 0.026 kilograms. Or in other words, it's 26 grams. Or 2.6 times 10 to the power negative 2 kilograms. And so we can see just how dense a neutron star is. I mean, it's basically on the verge of being a black hole. If it got any denser, it would reach its like Schwarzschild radius and it would just collapse into a black hole. But so it's about 10 to the 15 times denser. Or in other words, it's about a quadrillion times denser. So yeah, that's pretty impressive. And so that's how you solve a problem using density. So the main formula I used really was just that density is mass over volume. And keep in mind this is a rho, not a p. P is for pressure, which I will introduce later. I don't, depending on how time goes, I might even introduce in this video. we'll see. And so yeah, this by the way, density is applicable not just to fluids but also solids and liquids and gases. I don't know about plasma. We don't really learn about that here. Okay, so what's next? Okay, so another thing is that denser objects always float over less dense objects. Actually, sorry, it's the other way. Less dense objects always float over denser objects. Okay, so just as an example, the density of corn syrup, which I will abbreviate as CS, is 1200 kilograms per cubic meter. And the density of water is 1000 kilograms per cubic meter. And usually for liquids, the density is more or less constant. It can increase or decrease a little as the temperature increases or decreases, but not by much. And for water, it's actually around 997, but it's a lot more convenient to approximate 2000. So yeah. Okay, so since corn syrup has a higher density, if we were to put these two into one container, the water would actually float above the corn syrup. And this is also why ships float instead of sinking. A huge misconception that some people have is that heavier objects and lighter objects float. But obviously, ships are not by any means a light object, and they float, whereas a pin would sink if you put it into water. Not accounting for surface tension, which is not really taught in this like class, but that's something else that I might get to eventually. I don't know. Anyways, so yeah, so water would float above the corn syrup since it is less dense. The corn syrup would sink since it's more dense. That's why ships float because if you had a ship is heavy, but it's also huge, so there's a lot of mass. And I mean, heavy is for weight, but it's directly proportional to mass. So that's why ships are massive, but they still float because they also have a huge volume. So overall, the ratio of mass to volume for a ship is actually less than that of water. I mean, 1,000 kilograms in a cubic meter is actually a lot. Right? Yeah. Okay, so with that being said, a general rule of thumb is that like the solid version of something is less dense than the liquid version. So if you put a solid, I don't know, like I can't think of. I don't want to say water because water is actually the exception to this rule. So icebergs float because icebergs are actually less dense than liquid water, and they're actually like an exception because they're the only solid version of something that's less dense than the liquid. Generally, solids are the densest, liquids are the second densest, and gases are like the least dense, with the exception of water. So yeah, in fact, the density of ice is actually about 917 kilograms per cubic meter, and for water it's like 997. But it's just easier to round 2000. So it's not that much like denser, but still denser. So yeah. Okay, so now that we know what density is and how it affects like which objects float, and also actually before I move on, I'd like to say that this applies to all fluids. So this applies to gases as well. So less dense gases float, whereas more again more dense gases like staying lower, which is actually why balloons float. Because even though you have the solid material around the helium, the average density is still lower than that of the outside air, so it goes up because helium is like super non-dense, I guess. So yeah. Okay, now we're going to talk about pressure exerted by a fluid. And yeah, so let's just say we have a bottle of water. I'm not exactly an artist, so it's going to be trash. Okay, just pretend that this is a half decent drawing. I know it isn't, but bear with me. And let's say we poke some holes at the same level, at the same depth. Well, what should happen is that the water should spread out at the same rate. That implies that the pressure at that is constant at any given depth, which is true. Which means the pressure should somehow be related to the depth. And as we shall soon see, this is indeed true. So, also let's say that the bottle's open, so that we have air pushing down. So we're gonna introduce our first major rule that is, well, apart from density. But density is one of those things which defines itself. I mean, density was made to be mass over volume. This is something that was discovered empirically, and that is Pascal's first law. And so Pascal's first law, okay, so Pascal's first law states that an increase in the pressure of a static enclosed fluid in one in one place in the fluid causes a uniform increase in pressure throughout the fluid. Okay, did I skip something? Okay, give me a sec. Okay, never mind. I did not skip anything. So yeah, that's Pascal's first law. And so one application of this we see every day is actually a hydraulic lift. So actually, I'll just write as P1 is equal to P2. So an increase in pressure. So pressure is basically like changes so that it's constant throughout a fluid. Okay, so just as an example, let us draw a hydraulic lift. Okay, so let's say I have a narrow chamber here and a wider chamber here, and these both have pistons like this, and let's say I have a car on top of this, because that's what they're actually used for. Car mechanics will use hydraulic lifts to lift up cars so that they can work on the cars, uh, especially the underside of the car. So pressure, the formula for pressure is just the amount of force over an area. And this just means that the force is perpendicular to the area, or the component of the force which is perpendicular to the area. If the force itself isn't perpendicular. Let's say hydraulic lifts are actually super useful. They're used by auto mechanics to repair cars, to raise and lower them. And by Pascal's, excuse me, by Pascal's law, we can see that. So if we fill this with some fluid, like so, we can see that if we apply um, a small force here, but to a low cross-sectional area, it would equate to a large force over a larger cross-sectional area, since the increase in pressure has to be uniform. So then let's just say, let's call some force we're exerting here F, force 1 on lift. Yeah, I gotta pull out the fancy cursive, you already know. Anyways, and let's call this cross-sectional area 1. And let's call force that pushes this car up now force 2 on lift, and this has cross-sectional area 2. So by Pascal's law, we'd have to get that F1 on lift over A1, since pressure is force over area, has to be equal to force 2 on lift over A2. And so we can see that we can easily raise a car actually just using the power of fluids, because if we apply a small force but over a really small area, then that just equate to a large force over a large area, which is pretty cool. And we can actually find force. Actually, sorry, this would be force lift on 2, because now the lift is exerting the force. Because then this would be equal to, if we just rearrange terms, we get A2 over A1, where A2 is like significantly greater than A1, times the first force. And so we can see it's extremely efficient. Like you don't need to be a whole to lift cars. It's just a case of brain cell drawings, I guess. But yeah, and so this is all just one container, but the cross sectional area here is wider than here. So yeah, and so that's just a useful application of Pascal's first law. And actually, I randomly brought up the bottle example, but going back to it, if we had an open bottle, then you'll so if our bottle is open and you were to poke holes all throughout it, you would notice that the water would spread out slower as it's closer to the top, but when it's closer to the bottom, it would spread out with a higher velocity, sort of like this. And so we can see that as depth increases, the pressure must also increase. And yeah, and we can sort of think of this to better help understand why this is the case. We can think of this as analogous to a stack of books. So if you have like a stack of 4 books, so we'll call this 1, 2, 3, 4. Book 4 only has like air pressure from air on it, but book 3 now has pressure from the air and book 4. Book 2 has pressure from the air. Book 4, book 3, and book 1 has the most pressure from all 3 previous books in addition to the air. So similarly with water, um, pressure increases as you go deeper. And yeah. Okay, and we can actually find how pressure changes between any two depths depths by using Pascal's second law, which was actually I'll just erase all of this, or I'll just erase the hydraulic stuff since I already covered that. Okay, so Pascal's second law is not as conceptual, it's more quantitative, but it states that P sub 1 is equal to P sub 2 plus the density of the fluid times y sub 2 minus y sub 1 times g. And yeah. So as you can see, this doesn't necessarily show how pressure changes with depth. It shows how pressure changes with a variation in depth. So as you go deeper, so by the way, y is not the height; it's the depth in this case. So if we have some container, y sub 2 would be deeper. And actually, let's say that y sub 2 is deeper than y sub 1. And P sub 2 is the pressure at Y sub 2. Actually, I'm sorry. Let's assume that Y sub 2 is above Y sub 1. So Y sub 1 is at the deeper depth. Okay, so this is Y sub 1, and this is Y sub 2. So now let's say that the pressure here is only P sub 2, and we want to see what the pressure here is going to turn out to be. And we know what the density of the fluid is. Then all we have to do is subtract these to find the change in depth, multiply it to the density of the fluid, and then to the gravitational constant, and then add that to the original pressure. And we can use this formula to derive a formula on how pressure changes with depth uh, if we start from the top, obviously. So and that formula is just the pressure is equal to the atmospheric pressure plus rho plus g plus h. And h is the depth, not the height. Or alternatively, I personally prefer this formula. It's plus rho g delta y, where this is the depth. And yeah, and so that is Pascal's second law. And yes, I think that's it for um, static fluids, I believe. And yeah, and by the way, atmospheric pressure, I almost forgot. Atmospheric pressure is equal to 101.325 kilopascals, or alternatively 101,325 pascals, which, since pressure is force over area, is equivalent to newtons per meter squared. So yeah, and most people just approximate it to 101,000. Some even use 100,000 because that's easiest. But yeah, so that's just that. That's what atmospheric pressure is. Okay, and now we're going to be discussing buoyant force. So, let me just do this like this. Okay, so yeah, as we said earlier, that's the formula for pressure. Basically, whenever you have an object in the water, so just, okay, so whenever you have an object in the water, there's going to be a force. There's obviously going to be gravity, which is pulling it down. So that's mg, or because of our formula with density, we can rewrite this as the density of the object times the volume of the object times g. But there's also going to be a force resisting this, or going against it. It's called the buoyant force. And now the buoyant force, the formula for that is the density of the fluid times the volume of the object, or in other words, the volume that's displaced by the object times g. And so we can see that if the fluid was denser, the object would have to float because the buoyant force is greater than the gravitational force, which makes sense, which is consistent with my example with the water in corn syrup. And if the object was denser in the fluid, then it would sink. And so yeah, that's just So this is the formula for buoyant force. And it's so buoyant force. And keep in mind that this is just the amount of fluid displaced by the object. So in essence, what you're really going to see what's heavier. The volume of the object in terms of the fluid, or like the amount of fluid displaced by the object, or the object itself. And if the object's heavier, then, or if the object's more massive, yeah, if the object's more massive, then the object will drown. If not, the object will float. And so yeah, that's how buoyant force works. That's why diving boards, or not diving boards, what's it called? Like kickboards float, and like metal stuff generally sink. And yeah, so that's how you can determine, I guess, if you know the density of an object and the density of a fluid, that's how you can determine whether or not an object will sink or whether it will float. And interestingly enough, that's this is kind of how submarines work. So they actually have compartments that they can fill themselves with water, and so ordinarily the submarine is not as dense as water, so it floats. As it fills itself with water, it starts to sink as it gets denser, and then the water, and as it fills itself with more and more water, it sinks more and more. And you might be wondering, wait, how does it sink though if the water has the same density as water? Like, shouldn't it still float? And the reason for this is so if I have a submarine, it's made completely out of metal, but the inside is filled with air. So the average density makes it less dense than water. But if you add water and metal on the exterior, which is denser than the water, then the average density is actually greater than that of the water, which makes it sink. And yeah, so that is why submarines are able to like float and sink. And so those are pretty much just the basics for static fluids. So I went over pressure, density, Pascal's first and second laws, and Pascal's first law's application to hydraulic press, and also buoyant force. And actually, this video took longer than expected, so I might have to make another video for talking about fluids that aren't static, or in other words, fluids in motion. Actually, let me just check real quick how long that chapter is. Um, because if it takes a while, then yeah, I'm probably going to accept the video. And yeah, the chapter actually looks kind of long, so I think I will be making a separate video for this. And so the summary is basically going to just be, first I'll talk about fluids, so fluids in motion, and then this is for static fluids. And then I'm going to move on to gases and like kinetic theory of gases, and then thermodynamics, and then electricity, and then magnetism, and then optics, and finally like modern physics. If there's time, because the exam's on the 10th, it's currently the 7th, so I have 2 days to cram for it, and hopefully it goes well. And yeah, with that being said, thank you all for watching, and yeah, I'll see you next time. Peace.